morning, good afternoon, good evening, wherever you are watching this presentation from, and thank you for coming. Before I get started today, I'd like to tell you a little story. A while back, I was pair programming with one of the other developers on my team. We had been tasked with adding some new functionality to an existing piece of our code base. And we found where the existing functionality was, and it was one big method, kind of a tangled mess. We could have tried just fitting our new code in and hoping for the best. Or we could take the time to try and figure out what everything was really doing and find the best place for our new code to go. And I started identifying things that could be made into helper methods. And I found some variable checks that we could do a lot earlier in our code, so we didn't have to run calculations unless we actually needed them. And as I'm pointing these things out, my coworker turned to me and said, "How do you even know where to start doing this?" And I realized that this was something that a lot of people were probably interested in doing, not just in should I refactor, but how and where. And so refactoring, otherwise known as saving your code from yourself. My name is Lorien Rensing, and I am a software developer working primarily in C# and JavaScript. So when we get to the examples for this talk, you will see them all in C#. But the principles really apply to any programming language. So to start off, let's get some common definitions of what is refactoring. And the best place to figure this out is to go to the man who wrote the book on refactoring, Martin Fowler. And I do mean that literally. His book, Refactoring: Improving the Design of Existing Code, is now in its 2nd edition. He defines refactoring as a change made to the internal structure of software to make it easier to understand and cheaper to modify without changing its observable behavior. And we'll come back to some of these principles later on in the talk. But honestly, this is kind of a long, complicated definition. So a simpler one would be from Dr. Rebecca Parsons, author of The Evolution of Evolutionary Architecture. She defines refactoring as a small behavior-preserving change. And this is a little easier to understand. It's a small change. It's not a full rewrite of your software. And it's behavior preserving. It does not add new functionality. It doesn't fix any bugs. The behavior when you start and when you end should be exactly the same. So refactoring is also a verb. Back to Martin Fowler, and it's to restructure the software by applying a series of refactorings, that's our noun from before, without changing its observable behavior. So where does refactoring fit into the software development process? Kent Beck, who was Fowler's co-author, defined this process as make it work, make it right, make it fast. Refactoring is part of step 2, where we make it right. So that covers what refactoring is. Now we need to move on to, well, what does make it right mean? Or in another way, how do we know what's wrong so that we can make it right? For that, we want to look at something referred to as code smells, which is a term coined by Kent Beck again. And it's defined as a surface indication, usually corresponding to a deeper problem in the system. So there's a couple things that code smells have in common. First, they're pretty easy to spot. If you have to go digging for something, that doesn't mean it's not wrong. It's just not a code smell. And the other thing is that code smells don't always mean that there's a problem. Just like in real life, you might have a very obviously black and white striped skunk, and that stinks, and you definitely don't want it around. But another stink could be coming from well-aged blue cheese, and it's supposed to smell like that, and is not actually a problem. So now we'll move on and take a look at a sample method that we'll go through and identify some code smells in, and then see how we can refactor it to make it into a better program. And for this example, we're going to be using a method that calculates the monthly payment for a mortgage. This is the method that as it originally existed. And you don't really need to try to read every line at this time, because just looking at the code by itself gives us a code smell. Our code smell here is that this is a very long method. This particular method is 61 lines. For reference, at my usual screen resolution, I can generally get 30 lines of code on the screen at once. I actually rotated my monitor into a vertical orientation in order to fit everything on the screen to take this screenshot. Now, this is working code. It passes its units tests, but it's very long. It's trying to do everything in a single method. As Bill Gates once said, measuring software productivity by lines of code is like measuring progress on an airplane by how much it weighs. And it's very easy to add lines of code, but that doesn't necessarily mean the software is any better. Much like you can add weight to an airplane by filling it with bricks, but it won't fly any better. So let's start breaking down this long method and see what other code smells we can find. Starting at the very beginning of the method, we have a very vague method name, calculate. And although we know that this is a mortgage payment calculator, if all we had to go on was this method, that wouldn't be obvious from the name. We've got 4 parameters. Since C# is a statically typed language, we know what the types are for our parameters, but we don't know what any of them actually do from their names. Our variables, looking just at the variable names, are every bit as bad, more single letters with no particular meaning. Now, we have comments that can tell us this, but what we want to see is code where the comments are not necessary because we have names that communicate what we're trying to convey in our method. Your code should be easy to understand without the comments. If you have to ask why it's doing something, it's generally already a problem. Now, this isn't to say that all comments are bad. There are occasions where you may need to have a comment, for example, to define a certain amount of business logic, or to explain that this is code that comes from, say, a one-based index passed into something that expects a zero-based index. And this is the calculation that normalizes the two. But this should be the exception rather than the rule for comments. Moving on a little further, these are the next two blocks of code. And from our comments, we know that this is a power formula for the numerator and a power formula for the denominator. As it happens, for our mortgage interest calculation, we do have to raise something to a power. And this is not a built-in part of C# for the decimal object type. So we've written our own, and we've written it twice. And we've written it with slight differences, but basically doing the same thing. So rather than duplicating our code, what we would rather do is see everything in one place rather than repeating it. In this case, we could make it a helper method. And this follows a principle called dry. Don't repeat yourself. Once you know you will need to use the same piece of code over and over in multiple places, it becomes worth pulling it out into a helper method, or sometimes even a helper class. That way, anytime you need to use that method, you know that it will always work the same way because you're always calling the same thing. Moving on to the next section of our code, we have something that's not quite as obviously wrong out of context. We're preventing a divide by zero error with an if block. And if the if block isn't necessary, we go on to our final calculation. However, if you remember our variable names from the previous slides, which, as bad as they are, I understand if you don't, we have actually calculated some of these values well before we actually use them in our else block. Which means that if we do fall into our if block, we've done our calculations when we didn't really need to. This is a sign of poorly organized code. We can move our guard clause, which would be the if statement that prevents our divide by zero, much earlier in our code rather than running through our power formula. Now, this isn't necessarily wrong. It won't break our code. But much like you could find your lost key if you knew it was in this drawer, it would be a lot easier to find if it was well labeled and well organized on a rack of pegs for each individual key. So now that we've identified some places where our code could be changed, how will we know if these changes are actually making a difference? And to do that, in Visual Studio, there are actually code metrics that you can look at to see what the quality of your code is and possibly where there is room for improvement. These metrics are calculated at the solution, the project, the class, and the method level. However, they tend to be most valuable at the method level because that's where we can make the most granular changes. The first metric we'll look at is the Maintainability Index. This is defined as the relative ease of maintaining a given section of code. And this is not so much a single metric as it is a calculation based on the other metrics in this system. Microsoft provides a convenient color-coded scoring system. 0 through 9 is coded red for very unmaintainable code. We definitely want to avoid having code at this level. 10 through 19 are yellow. It could be worse, but it should probably be fixed before it gets worse. 20 to 100, they code as green. And that's a pretty big spectrum of what they consider maintainable code. When I'm looking at things for my own reference, I generally target a maintainability of 50 or better and consider that to be my green zone, and let 10 through 49 be my yellow zone. Maintainable software lets you fix bugs more easily. It lets you add new features more easily. And if you're a professional developer, let's face it, it lets you spend more time on new work, which is where the fun stuff usually is. The next metric we'll take a look at is called Cyclomatic Complexity. This is defined as the number of distinct paths through a method. Generally, we have a target of less than 10 paths through any given method. More paths through a method make it harder to understand and easier to miss something, either in missing where a bug is located or in how the code is expected to behave. The lowest cyclomatic complexity we can have is 1. There's only one way to get through the method to our return value. For instance, a simple sum function. We take in 2 integers, we return the sum. There is no branching logic, no if statements, one path through the method. Almost as low is a very simple method. In this case, find larger. We have 2 paths through the method. Either the second integer is larger than the first, in which case we will return the second integer, or the second integer is not larger than the first, and we will return the first integer. 2 paths through the method. This determined language method has a cyclomatic complexity of 6. It's based on an actual method we use at my work, wherein the language a page is being displayed in could be based on a query string, or a cookie set in the browser, or the browser's native language. So we have 3 parameters, and each parameter either has a valid value, as defined in our list of supported languages, or it does not have a valid state. So we have 6 total paths through this method. And in this case, not only do we have our if blocks, but we've also got a shorthand notation at the end of the method on our final line. This also is considered a pair of paths through the method. Finally, we have a method with very high cyclomatic complexity. The font on this is scaled down pretty far, so I wouldn't recommend trying to read it right now. But one thing to notice is how much indentation we have. At some points, we actually have 7 levels of nested if statements. If you are interested in taking a closer look at this, It's from a kata called the Gilded Rose, which is specifically intended to practice refactoring highly complicated code like this into something with much less complexity and that is much more maintainable. As a hint, when you're developing your unit tests, you can use the cyclomatic complexity as a rule of thumb for how many tests you need. Your number of tests should cover each path through the code. So in that case, you presumably will want to have at least as many tests as your cyclomatic complexity. Our final metric is the number of lines of code. And this one is not quite as obvious as it seems, because it only refers to lines of executable code. It does not refer to any white space. It does not refer to any comments. And it doesn't apply to any curly braces that are on their own line. This is a pretty simple metric to understand, and it's pretty easy to see why we would want to lower the amount of lines of code. If we have more lines of code, that means we have more code to maintain. So these are the metrics we had on that original code sample. Our maintainability index was 49, good by Microsoft standards, not quite good enough by mine. A moderate cyclomatic complexity at 6, and 26 lines of code, executable code. So let's start working our way through this method and see what we can improve. We can start at the beginning with all those terrible names. By changing calculate to calculate monthly payment, it becomes much more obvious what this method is supposed to do. Likewise, our parameters and our variables are now spelled out what they actually mean. And while you can see the relationship when you compare them, for instance, our original parameter of Y has become years in mortgage. Years in mortgage is much easier to understand. Additionally, Visual Studio has some built-in tools to allow you to rename variables and parameters, and it will make the update to every usage of that within the scope. This is helpful because it means that you don't have to worry about forgetting to make the change in one place or accidentally misspelling something. Overall, this is a very safe and simple fix because we have not touched any logic. However, it hasn't actually changed any of our code metrics. It is, in theory, more maintainable because the variable names are more meaningful, but meaningful is not really something that can be automatically calculated. So let's see if we can make a change that will actually improve these metrics. Remember our duplicated code? Let's extract that into a helper method. Since this code is doing the same thing, we can use one helper method to calculate it in two places. So on this page, x is the power result in the numerator and z in the denominator. When we refactor it, we've got better names, so numerator power, formerly x, and denominator power, formerly Z. And in both cases, we are calculating it using a helper method, raised decimal to power of term, which is a part of the standard payment calculator on a loan with interest. And it gets used in two places, the numerator and the denominator. To make this even simpler, there are automated tools you can also use to extract a method by selecting it in your code. I believe the shortcut is Control-R, Control-M, where it will automatically identify what your variables are that need to become parameters, what your return type needs to be, and it will swap in a call to your new method in place of the previous code block. So that's what we have done here. Now we're following the dry principle. We're not repeating ourselves anymore. Since this is still existing code, it's a pretty low risk refactoring that we can do. We're not likely to introduce a new bug with this change. So let's see what our code metrics say now. After step 2, our maintainability index has gone up to 55. Our cyclomatic complexity has gone down to 4. And we've dropped the number of lines of executable code in our original method down to from 26 to 16. So if you look at the trend lines, we can see that from just this change, our maintainability index at the top has gone up, and our lines of code in green at the middle and cyclomatic complexity in red at the bottom are both trending downward. And this is what we want to see. So for those of you who have to justify these changes to bosses who really like numbers and really like data, here it is. We've got definite improvements. Moving on, we can actually extract still more methods. In this case, our helper methods will replace the first half and the second half, calculating the full numerator and the full denominator. This is a change we make primarily for readability, because it will allow us to read through our code, and instead of calculating a numerator power, calculating a denominator power, etc., we can actually calculate those as full items. Numerator, denominator, and we have a helper method that calculates our power. For the numerator, we multiply it by our interest rate, and for the denominator, we subtract 1 according to our equation. So as we move through the method based on the length of our mortgage, we make our calculations. This allows us to have what's known as self-documenting code. Each step has its own self-contained method, and if we use good names, like we did in step 1, these methods will tell us exactly what we can expect to have happen inside the method. This didn't really change our code metrics. As you can see, they're the same between step 2 and step 3. But much like our first refactoring, they make everything easier for a human to read. Finally, we had this disorganized code section with our guard clause that was coming very late in the method, almost to our return statement. So we had done quite a lot of potentially unnecessary calculations before we even checked. After we've reorganized things, we have here our entire method. Our first guard clause comes very early. We need to know how much we have financed on our mortgage. If we have no years in our mortgage, we immediately have to pay back what we would have borrowed. Likewise, if we have a zero interest rate, we don't need to do any fancy calculations. We simply divide the amount we financed by the number of months in our mortgage, and that's our monthly payment. So now, after we've checked those two cases, we can go through and use the calculations that we've defined in our helper methods to figure out our numerator and our denominator, divide them, multiply by our principal, and we have our monthly payment. The arrows indicate what are called guard clauses. Basically, they check for a particular value, usually a special one. In this case, we're checking for 0. This can do things like prevent divide by 0 errors, or simply return something without calculating it. You can also guard against, for example, getting a null value where you don't expect one, and thus avoiding the dreaded null reference exception. This will both improve the performance of our method in only doing the complex calculations when we need them, and it makes unit testing much easier. It's also a riskier change because if you were to move these guard clauses to the wrong place, you could actually end up in exactly the situation you were trying to avoid. If you have unit tests, they will generally catch something like this before your users do, however. And when we check our code metrics for this final refactoring, our maintainability index has gone up to 56, our cyclomatic complexity has gone down to 3, and we're down to 15 lines of executable code in our calculate mortgage payment method. And once again, our trend lines continue to move in the correct direction. So we can see that we have made some positive changes in this code. So that covers how we refactor our code, but it doesn't necessarily cover when you should refactor the code. Is this something you should always be doing? Should you set aside a specific time to go in and do it? When should you refactor? I find one of the easiest times for refactoring code to be what's called opportunistic refactoring. You're already in the code. You see something that could be improved. Since you're right there anyway, take the time to make things a little bit better. After all, you're already working in that code. You should also try to leave your code better than you found it, also known as the Boy Scout rule. Your code might be pretty good to start with, but if you're changing it, don't just leave the changes in that first working state. Go back, take a look, clean it up, make it better. At several points, I've mentioned using unit tests to verify that your refactoring has not actually changed the behavior of your code, which is great as long as you have unit tests. But in the real world, unfortunately, not everyone has unit tests on all of their code. So what do we do in that case? The easiest thing to do is start writing the tests for brand new code. A clean slate is the easiest point to start adding unit tests. Ideally, you would write this code using test-driven development, where you would write your unit tests first, or at least write new code intending and expecting to test it. In existing code, you can try and find a spot where you have an obvious place to test. Start testing there and build from it. You won't necessarily cover every path, but it will be better than you had before, and it will give you something to build off of in the future. And when all else fails, you can use what are called smoke tests to cover your existing code. This usually involves going through the system in much the same way that a user would and looking to see what breaks. They're pretty good at telling you something is wrong, but not so good at telling you what specifically is wrong or why. This definition has come from two different places that I've heard of. The first is in testing physical systems of pipes or hoses. You have an entrance and an exit, and in theory, it should be a closed system between them. So if you cover the exit, put smoke in at the entrance, nothing should come out. If smoke does come out, you have a leak at that point. That's a problem, you need to fix it. But it doesn't tell you why you have the leak. The other source I have heard for this term comes actually from electronics hardware. If you've ever seen a circuit board go bad and fail, a lot of times there will be a small pop and some blue smoke will escape. The joke being that the hardware won't work without its blue smoke. So you need to make sure your software likewise has all its blue smoke properly contained. This has just been a surface level look at what refactoring is. And there's a lot of resources. Martin Fowler, of course, who wrote the book on refactoring, has his own website with a variety of articles and definitions that are related to this. Sandy Metz has written an ebook, 99 Bottles of Object-Oriented Programming, which takes you through refactoring a program that will generate the lyrics to 99 bottles of beer on the wall, starting with 1 bottle of beer up through an infinite number. And there are samples available in multiple languages, Ruby, JavaScript, and PHP, depending on what you're most comfortable working in. Ardalis.com has an excellent article for when you should refactor that I did use as a big source for that section of this presentation. And the author of that post also has a course on Pluralsight, refactoring for C# developers. The tooling I used was specific to Visual Studio. There are some other tools. There is a program called NDepend that does a variety of in-depth metrics for .NET. Now, as I mentioned, things like cyclomatic complexity and code maintainability are calculated by Visual Studio at any level from the solution all the way down to the method. But the problem is, once you get above, say, the class level, things like cyclomatic complexity or lines of code don't become very helpful if you have a solution that defines a lot of objects. You might have a lot of lines of code, but each line of code might be simple definitions of properties with getters, setters, and no real logic beyond that. Likewise, something that has a lot of class files with a lot of methods in them might have a lot of paths through the solution, but any given use case might only need to go through a few of them. End-depend will let you run more complex calculations on these methods and get a similar result for your entire solution. If any of you are familiar with JetBrains, they have a number of IDEs with built-in code metrics. They have a refactoring tool for Visual Studio called ReSharper that I am very fond of. It lets the tool do the heavy lifting of extracting methods and renaming variables and all sorts of useful things like that to make my code just that much better without having to work at it. If you're working in Visual Studio Code, there is a Code Metrics plugin that lets you calculate similar metrics for JavaScript, and this is available for free to add to Visual Studio Code. So I hope this has given you some inspiration for things to go out and improve in your own code. I hope you've learned something from this talk. I look forward to hearing from you. Thank you.